In this paper, we propose a generative framework for part-aware dexterous grasp generation. And in this video, we sequentially introduce the framework, depict the generated grasping poses, and showcase the actual performance on a real-world platform. Specifically, our framework consists of three key components, which form a unified generative framework that is fast, controllable, and semantically aware. The core insight is that a dexterous hand is not a monolithic structure. It is composed of anatomically distinct parts, containing the palm, the thumb, the index finger, the middle finger, the ring finger, and the little finger. Building upon this representation, we train a separate VQVAE encoder for each part. Each encoder takes the surface points of its corresponding hand part and maps them into a discrete codebook index. This gives us a compact, structured sequence of 6 tokens that represents any dexterous grasp configuration. Once we have this token sequence, we train a bidirectional MaskDexGrasp transformer to predict masked tokens conditioned on 3 inputs: a task embedding from a task ID, a text embedding from a natural language instruction encoded by CLIP, and an object geometry embedding from a PointNet encoder. This allows our model to generate grasps that are both geometrically compatible with the object and semantically aligned with the task description. During inference, we start from a fully masked token sequence and iteratively unmask tokens with highest confidence scores, progressively refining the grasp over T steps. In addition, to support the training and evaluation of our framework, we construct a dataset by consolidating grasping data from 2 established hand-object interaction datasets. In total, it includes 64,891 high-quality grasping instances, 2,296 object models, 11 task categories, and 259,564 textual annotations. We perform retargeting process in 2 stages. First, a joint-level retargeting that optimizes shadow hand parameters to match the 3D fingertip positions. And second, an energy-based refinement that minimizes self-penetration and object penetration losses to ensure physically plausible interactions. For textual annotations, we use the Quen VLM, which takes a rendered image of each grasp and a concise action object description as input, and generates 4 linguistic variants per grasp, covering basic, present, progressive, and passive tenses. Here we present a gallery of grasps generated by our method. We can observe that the fingers wrap naturally around the object surface with no visible interpenetration. This slide shows additional generated grasps on objects such as cameras, rounded bottles, and toothbrush, further demonstrating the generalization of our method. Besides above, our method also generates multiple diverse yet semantically consistent grasps for the same object and text description. To validate the actual performance beyond simulation, we deploy our system on a real robotic platform consisting of an X-Arm 7 robotic arm and a Freedom 5-fingered dexterous hand. Here we show real-world grasping executions on a mug, a power drill, and a dispenser, played at 4 times speed. In all 3 cases, the robot arm smoothly approaches the object, positions the dexterous hand according to our predicted grasp, and successfully lifts the object without dropping it. This slide continues the real-world demonstration with different objects, including a water bottle, a pair of binoculars, and a frying pan. Thanks for watching.